In this video, I am going to discuss about the derivation of the Ohm's law, or this one is electrical resistivity and conductivity. Let us consider a conductor. Suppose this one is a conductor, and length of this conductor is L. Suppose length of this conductor is L. Area of cross section is A, and when a potential difference V is applied across the end of the conductor, suppose the electron inside the conductor start to move with the acceleration A. If m be the mass of the electron, then the acceleration of that electron inside the conductor A is equal to F by m, where F is the force experienced by the electron inside the conductor when a potential difference V is set up across its end. Already I have told you, when a potential difference V is set up, then an electric field is developed inside the conductor, and due to that electric field, the electron inside the conductor will start to drift. And suppose the acceleration of that electron is A, so A is equal to F by m, and at place of F, we can write F is equal to QE, so magnitude of that force E, where E is the charge on the electron and E is the electric field set up inside the conductor, so E upon m. So this one is the acceleration, and electric field inside the conductor E is equal to V by L. So now we can write this is equal to E by m into V and by L. It means the acceleration of the electron inside the conductor is EV upon ml. And the drift velocity of the electron, already I have told you in the previous video, drift velocity of the electron inside the conductor Vd is equal to A into tau, where A is the acceleration of the electron and tau is the average relaxation time. And also we know the relation between current and drift velocity. We know that I is equal to N E A V D. This is the relation between the current and drift velocity. Or from here we can say Vd is equal to drift velocity Vd is equal to I upon N E A. But from here you can say, suppose this equation number 1 and this one is equation number 2. From equation 1 and 2, from equation 1 and 2, we can say here A tau is equal to I upon N E A. Or simply we can say at place of A, we can write from here EV upon ml. So at place of A here we can write EV upon ml. This one is A into tau is equal to I upon N E A. This one. And from here V is equal to, from here V is equal to, we can write here ml, V is equal to mli upon n E square tau and into A. When you will make the V as the subject of formula from here, then V is equal to, we can write here mli upon n E square A and tau. And from here, now we can say V is directly proportional to I, because m is the mass of the electron. For a given conductor, L is the length of the conductor, N is the number of free electrons per unit volume in this conductor, E is the charge on the electron, and tau is the average relaxation time, and A is the area. So from here we can say V is directly proportional to I. And according to Ohm's law, when V is directly proportional to I, then on comparing, and also we know V is equal to I into R by Ohm's law. So this term ml upon ne square tau, which is a constant for a given conductor at the constant temperature, and whole this term is called the resistance of this conductor. So when we compare this equation A and this equation B, then from equation A and B we can say here R is equal to ml upon n E square A tau, where R is the resistance of the conductor. And now you see here the resistance of a conductor is depends on, we can't be change the M for a given conductor and E tau. So R is directly proportional to L and inversely proportional to A. So the resistance of a given conductor can be given as R is equal to M L upon N E square A tau. And now next topic is specific resistance. Specific resistance or electrical resistivity, or electrical resistivity. I hope maybe all of you also familiar with this term. This term is not new for you. Is specific resistance, or that same term specific resistance is also called electrical resistivity. And the specific resistance or electrical resistivity is the ratio of intensity of electric field at any point within the conductor and the current density J at that point is called specific resistance or electrical resistivity of the conductor. So simply you can say here the specific resistance or electrical resistivity is the ratio of intensity of electric field at any point within the conductor to the current density J at that point. And specific resistance is denoted by rho, and it is given by rho is equal to E, where E is electric field intensity and J is the current density. So the ratio of electric field at any point within the conductor to current density at that point in the conductor is called the specific resistance. And also, you know, E is equal to V by L, and current density J is equal to I by A. So when we put the value of E and J in this formula, then rho is equal to V by L upon I by A. And from here we can write this one is V upon L into A upon I. And from here we can say rho is equal to V upon I into A by L. And all of you know, at place of V by L, V by I, by definition V by I is the resistance of that conductor. So we can write here rho is equal to R into A by L, where rho is the specific resistance or resistivity of a conductor, R is the resistance of that conductor, A is the area of that conductor, and L is the length. And if A is equal to 1 meter square, L is equal to 1 meter, and when we put this value here, then we can say rho is equal to R, and here 1 meter square upon 1 meter. So we can get here rho ohm meter. So we can define here a specific resistance is numerically equal to the resistance of a conductor for unit length as well as unit area of cross section of that conductor. It means if we take a conductor of unit length and unit area of cross section, then the specific resistance of that conductor is equal to its resistance. Now, the dimension of the electrical resistivity or specific resistance. We know that specific resistance or electrical resistivity rho is equal to R into A by L. So, the dimension of rho is equal to, already I have given you the dimension of resistance, which is M L to the power 2 T to the power minus 3 and A to the power minus 2. This is the dimension of resistance. Area L square upon length. Here we can write L. Now 1 L is cancelled by this one. 1 L is left. And now the dimension of rho is equal to, we can write M L square into 1 L here. So M L cube T to the power minus 3 and A to the power minus 2. This is the dimension of a specific resistance or electrical resistivity. So in this way we can find either unit or dimension of the specific resistance. And one more thing here, the specific resistance of a wire depends on the material of the wire. It means the resistivity or the specific resistance is the characteristics property of the material, and for the conductor made of the same material, a specific resistance is same. Suppose one wire of copper of this length and other wire of the same copper material of this length. Suppose their length is different, then their resistance will be different, but their specific resistance will same. Why? Because both is made up of the same material. So specific resistance or resistivity depends on the material of the wire. Since a specific resistance rho or resistivity rho is equal to R into A by L. And specific resistance can also be given in terms of materials parameter like mass of the electron, number of electrons per unit volume in the conductor, average relaxation time. In that term also the specific resistance is given. How? Rho is equal to R into A by L. Now at place of R we can put ML upon NE square A tau. So we can write here rho is equal to, at place of R, ML upon NE square A tau into A by L. A by L. Now L is cancelled by L, and here A is cancelled by A, and now we will get here M upon NE square tau. It means the specific resistance or resistivity can be given in terms of materials parameter like rho is equal to M upon NE square tau. Now mass of the electron constant, charge constant, average relaxation time at the constant temperature. If the temperature is constant, then tau will also constant. Then rho depends on N. N means number of electrons per unit volume inside the conductor, and for a given conductor N is same. Due to this reason, specific resistance depends on the material. It does not depend on the length, or it does not depend on the area of cross section of the wire for the same material. So in this way we can say a specific resistance is not changing by changing the length of the same conductor or the area of cross section of the same conductor. So dear student, today all of you go through this topic which just I have discussed in this video, and also from your book please you go through the specific conductance, because I want to tell you specific conductance, specific conductance. And a specific conductance is the reciprocal of a specific resistance. So simply you can say the reciprocal of a specific resistance is called a specific conductance, and it is denoted by the sigma is equal to 1 upon rho. And the unit of this specific conductance is ohm meter per inverse. Or we can also write this one is mho per meter. So in this way we can find the specific conductance and its unit, and the dimension of specific conductance, the dimension of sigma, dimension of sigma. So simply the reciprocal of dimension of specific resistance. So simply we can write m to the power minus 1, L to the power minus 3, T to the power 3, and A to the power 2. This is the dimension of the specific conductance. So in this way, we can find the dimension of specific resistance or specific conductance, and also you can write its unit in terms of these fundamental quantities. So please all of you go through this topic which just I have discussed. In the next video I will give you the Ohm's law in vector form. Thank you.